Hello, myself Sanjit Kumar Singh, lecturer in Electronics and Telecommunication Department at Praveen Patil College of Diploma Engineering and Technology. This is the fourth chapter, Radar Fundamentals of the subject Microwave and Radar. The topics to be studied in this presentation include basic block diagram of radar system, radar performance factors, radar range equation, and the factors influencing radar range and effect of noise. These topics will be covered in first part. Rest of the topics, pulse radar, antenna scanning, will be covered in second part, and the antenna tracking and antenna feed mechanism 4.5 will be covered in the third part. The marks allocated is 12 marks and hours, 8 hours of lecture. The course outcome after going through this presentation and the subsequent parts of this unit chapter, the learner will be able to interpret the radar based systems for range equation, range detection. Unit outcomes after completion of this unit, the learner will be able to describe with a relevant sketch the function of the given component of the radar system, calculate the maximum radar range for the given data, state the effect on the radar range for given parameters, explain with relevant sketch the given type of scanning and tracking methods used for radar communication, describe with relevant sketch the construction and working of the given microwave antenna. So these are the 5 unit outcomes of fourth chapter. So basically radar is an acronym that stands for radio detection and ranging system. So radar, the word radar was coined by US Navy in the year 1940. Radar is based on the principle that high frequency radio frequency signals are reflected by conductive targets, and this target usually happens to be airplanes, missiles, ships and automobiles. So basically an electromagnetic system used to detect the location and distance of an object from radar place is the radar technique. It works by radiating electromagnetic energy and into the space and monitoring the echo, the reflected signal from the objects. It operates in the UHF ultra high frequency, that is 300 megahertz to 3 gigahertz range, and also in the microwave range. The maximum range is determined by calculating the time taken by the signal, time taken in microsecond to travel from the radar set to the target and back to the radar set. So one of the equation is d is equal to t by 12.36, where d is the distance or the range in nautical miles and t is in microsecond. The 12.36 is the time taken by the radio frequency signal or radar signal to travel one round trip of 1 mile. So 1 nautical mile is covered in 6.17 microseconds. So for 1 round trip it will take 12.36 microsecond. So this d equal to t by 12.36. 12.36 is the time taken for 1 round trip for 1 nautical mile. So actually we are dividing the total time taken by the signal for 1 round trip. So total time divided by 1 nautical mile time round trip is 12.36, gives the range. The target's location is measured in angle from the direction of maximum amplitude echo signal the antenna is pointed to. Now to measure the range and location of moving objects, there is another Doppler effect used, in which the phase change between the transmitted and the received echo pulse is to calculate or evaluate the total distance and the angle of the target. So for the basic block diagram of an antenna of a radar system consists of a transmitter, a duplexer, a receiver, and antenna. The waveguides are used to connect the transmitter to receiver, transmitter to antenna, and antenna to the receiver. A duplexer is switching between transmitter and receiver if the common antenna is shared. And threshold decision circuit, this is for decision making. So let's see one by one. A transmitter, it can be a powerful amplifier like a klystron amplifier or TWT, traveling wave tube, or a powerful oscillator like a magnetron. The signal is first generated, the microwave signal or radar signal is generated with a waveform generator and then amplified in the power amplifier. The waveguides are transmission lines for transmission of the radar signals. And antenna, the antenna used can be a parabolic reflector, or it could be planar arrays or electronically steered phased arrays. Duplexer, what is a duplexer? A duplexer allows the antenna to be used as a transmitter or as a receiver. It can be a gaseous device that would produce a short circuit at the input to the receiver when transmitter is working. A receiver, the receiver can be a super heterodyne receiver or any other receiver which consists of a processor to process the received signal and detect it. Threshold decision, the output of the receiver is compared with the threshold, the reference, to detect the presence of any object. If the output is below this threshold or reference, the presence of noise is assumed. So here is the block diagram of a radar system: transmitter section, receiver section, the antenna system, and in between transmitter receiver is the duplexer working as a switch, microwave switch for the radar signal, and the received signal is given to a processor or decision making unit. And finally the display could be a scope type, or it could be the PPI type, or the target could be a spacecraft. Now the radar range equation. To determine the maximum range of a radar set, it is necessary to determine the power of the received echoes and to compare it with the minimum power that the receiver can handle and display satisfactorily. If the transmitted pulse power is PT is the peak value, and the antenna is taken as isotropic, then the power density at a certain distance r from the antenna is rho equal to Pt by 4 pi r square. Pt, the transmitted power, by 4 pi r square. But antenna is not only isotropic, mostly it is highly directional rather than isotropic. So if AP is the term used to represent the maximum power gain of the antenna, of the transmitting antenna, so the power density now becomes rho equal to AP multiplied with PT 4 pi r square. The power intercepted by the target depends on its radar cross section area or the effective area. So if this area is taken as S, the power impinging, power bombarding on the target will be P is equal to rho multiplied with the cross sectional area, effective area S. Rho into S is the power. So substituting the value from the above equation, we get AP PTS by 4 pi r square. target is not an antenna, its radiation may be omnidirectional, in all direction it could be any direction. So the power density of its radiation at the receiving antenna will be rho dash is equal to P by, again the same formula, P by 4 pi r square. So substituting the value of P in the from the our equation, we get AP multiplied with PTS by 4 pi r square whole denominator square. So like the target, the receiving antenna receives the portion of the radiated power that is reflected towards it, which is proportional to the cross sectional area of the receiving antenna. More the cross sectional area of the receiving antenna, more will be the signal. The received power is now P dash is equal to the density P dash rho dash multiplied with A0 will be AP PT S A0 by 4 pi r square the whole numerator square, where now this A0 is the capture area of the receiving antenna. So if the transmitting and receiving antenna happens to be same, then its effective capture area of the transmitting and receiving antenna is A0, maximum gain of the antenna is AP, and S is the effective area of the target, cross sectional area of the target. So if sum of the antenna is used for both reception and transmission, we have the maximum power gain AP is equal to 4 pi A0 by lambda square. So using this relation in the above, we get P dash is equal to 4 pi A0 multiplied with PT S A0 by lambda square 16 pi square r to the power 4. That can be further solved to PT A0 square into S by 4 pi r square r to the power 4 lambda square. So now the maximum range R max will be obtained when the received power is equal to minimum receivable power, minimum detectable power. So if that minimum detectable power is P min, so substituting that P min into the above equation and rearranging the terms for the R, when the power at the receiver is minimum detectable power, then we have the maximum range, and that maximum range R max will be equal to PT multiplied with A0 square into S, the effective area, by 4 pi the wavelength square multiplied with the minimum detectable power, the whole fourth root. So alternatively, that can be also written as by substituting the capture area A0 is equal to AP multiplied with lambda square by 4 pi. Into the above equation, we get PT multiplied with AP square into lambda square into S by 4 pi to the power Q, and multiplied with that is the minimum detectable power P min. So this equation, these two equations represent the most convenient method of radar range equation for ideal condition. Now there are number of factors which affect the maximum range. From the two equations itself, we can see R max, the maximum range is directly proportional to the having a fourth root relationship with the transmitted power. Then it has a relation, a square root relation with the capture area of the receiving antenna A0, and the fourth root of the effective area of the target. Then it is inversely proportional to the minimum detectable power. So lesser the minimum detectable power is, the radar range equation can be increased, the range capacity can be increased. So here this question has been asked, state 4 factors influencing maximum radar range, and the factors that are very prominent is the transmitted power PT. So in order to increase the range twice, in order to double the range, the power required to be raised to 16 times. Transmitted signal has to be raised 16 times. Means if we are initially transmitting 1 megawatt power, then we require 16 megawatt power to cover double distance, double range. Then minimum detectable signal, it also depends, the maximum range depends upon the minimum detectable signal. The P mean or S mean is, it is inversely proportional to R max is inversely proportional to the S mean, fourth root. So if we are reducing the minimum detectable power by increasing the sensitivity of the and the gain of the receiver, then we can increase the maximum range. But by reducing the minimum detectable power, we are exposing the receiver circuit, or it becomes more susceptible to the interference, as it is now it will amplify the weak signals rather than amplifying the low power received signals. So noise also gets amplified. So frequency and effective area of antenna is also on the factor, as R max is inversely proportional to the root of lambda, or R max is proportional to root of frequency. So that implies that increase in frequency increases the range, but in a parabolic antenna the beam width is given by the lambda by d. So if the diameter of the parabola is where d is the diameter of the parabola, if lambda is reduced, if the wavelength is reduced, beam width becomes very narrow, which reduces the tracking range of the radar. So this is particularly in case of a search radar, where the sweep of the antenna that covers a portion of the sky will require a longer time if the low beam width is very narrow. So thus radar frequency cannot be increased far too much, as the radar becomes ineffective although range may increase. Moreover, R max is proportional to root over AE, that is the effective area of the antenna. So in order to increase the effective area, diameter d of the parabolic dish antenna must be increased. Parabolic antenna must be increased, which in turn reduces the beam width. So drawback will be reduced beam width. So it also, the maximum range also depends upon the target cross sectional area sigma, or that is also the S in the previous equation we have seen here, 3.9 equation S value. So the radar cross section of the area is the area of the target as seen by a radar. The radar cross sectional area of the target is not a controller factor. So these were the factors on which radar range equation depends, or maximum area that can be covered by a radar depends upon. So those were at the normal condition, ideal condition, but noise is also one of the factor, how it is affecting the R max equation. Let's see, the maximum radar range is affected by the noise as it determines the minimum power that the receiver can handle. So for increasing the radar range, the minimum detectable power at the receiver has to be decreased, which in turn is dependent on noise figure F and the equivalent noise power generated at the receiver in R. So noise figure is given by F is equal to the signal to noise ratio at the input to the signal to noise ratio at the output. So that can be further solved to get the equation F is equal to 1 plus NR by NI. where Si is the input signal power, Ni is the input noise power, S0 is the output signal power, and obviously N0 will be the output noise power, and G is the power gain of the receiver. So we have we can rearrange the above F is equal to 1 plus Nr by Ni as only taking the ratio Nr by Ni on the left hand side and taking the F on the right hand side, or rearranging we get F minus 1 as the ratio of the Nr by Ni. So Nr can be written as within bracket F minus 1 multiplied with Ni. Now this Ni can be written as K T0 delta F times F minus 1. So what is this K T0 delta F? This is the noise input power of a receiver. So the minimum detectable power should be at least this noise input power of the receiver or more than that. So K, where K value is the Boltzmann constant and is 1.38 into 10 raised to minus 23 joules per Kelvin, the standard unit for temperature, and T0 is the standard ambient temperature, that is 290 Kelvin, and delta F is the bandwidth of the receiver. So if the bandwidth of the receiver is increased, then more noise interference can take place. So there should be a compromise, and the minimum receivable signal for the receiver under so-called threshold detection condition is equal to the equivalent noise power at the input of the receiver, as shown in the above equation, the previous equation. So Rmax can be written by substituting the P mean or S mean value as Pt times A0 square multiplied with the S and divided by 4 pi lambda square K T0 delta F multiplied with F minus 1, the whole 1 to the power 1 by 4, or the fourth root of the whole term. The above equation is reasonably accurate in predicting the maximum range. So in this way we see the noise affects the maximum range, and the other factors, transmitted power, effective area of the target, effective area of the transmitting antenna, and the ambient temperature also affecting the maximum range. So thank you for this patient listening.